Okay guys, so we're going to go through this example, page 321, just to discuss the application of your integrals to linear motion. Right? So I've written up there that you need to understand the difference between displacement from a point and total distance travelled. Right? Now, just like with differentiation, one of the biggest applications of all this stuff is displacement, speed, acceleration with respect to time. So if you differentiate or you integrate with respect to time one of those variables, you will get one of the others. So obviously differentiation, you go from displacement to speed to acceleration. Therefore, integration will take you from acceleration to speed to displacement. Okay, but what we've got to just talk about very quickly is this example. I think takes a little bit of getting your head around it, but it's not too bad. The difference between displacement and the total distance travelled. Okay, so we are looking at a particle that's moving, right? So you read through that. So we've got a function for a particle moving along a horizontal line, and it's given by st, right? T squared minus 4t plus 3, when t has got to be greater than or equal to 0. Just why is t greater than or equal to 0?
Isn't this
just time.
Isn't this the same as we did the f of the first, like the upper bound minus the f of the lower bound?
I don't know. I don't want to say no, because I don't really know what you mean by.
Well, we did, like when we integrated and then we put in the bound.
The area?
Yeah, the area.
Yeah, I mean, all this is the area under the curve, but we're just doing a little bit of talking about the difference between displacement and total distance, that's all. So it's basically the same thing. We've got a function that gives you, well, what is st? So displacement. Okay, do you understand the difference between the words displacement and distance travelled? Anyone not? You don't? So displacement, who would like to explain those that know?
I think the displacement is the vector quantity, and it signifies the direction, and distance is basically the scalar quantity.
I in this context, no, I wouldn't agree with what you just said actually, because direction has, well, distance travelled has a direction. You would, like you said, would treat it like a scalar quantity because total distance travelled doesn't matter which direction you go. But the problem is displacement is not the same thing, but with a direction. The numbers do change. Displacement is once you've done all your travelling, it's how far away you are from the starting point. Okay, so for instance, with this, we've got a starting position. Well, I've got a starting position here. If I walk to my desk and then walk back to my starting point, my displacement would be 0. So I guess like you were talking about vector quantity, I would have a vector quantity of a negative direction and then a positive direction, and it would end up as nothing. My total distance travelled is not nothing, is it? It's there and back. Right? The total distance, I have to add those two together and I have to take into consideration the negatives. And that is what we have to be really aware of with our integration, because obviously areas under curves are negative values, so they're treated differently when you want displacement or when you want distance travelled. So this is what we're looking at. So just to go through it quite quickly then, so you have in your book that function is there. So it's not really necessary to worry about, but we've got, if we integrate VT, so velocity is displacement, right? Between 0 and 2, because what they're saying is, well, what happens after 2 seconds? So this particle goes from this point, the blue dot, when it's t equals 0, so at point 3 meters beyond their control point of 0 meters, or whatever that means, we don't know. But it goes back towards that and then goes past it by 1 meter, and that's where it stops. So if we were to work out, you've done your integral stuff, how do you work out the area under the curve? Well, S of t between 0 and 2, you put 2 in, you put 0 in, and you work it out, and we get an answer of -4. Right? Are you happy with that? Yes. So that's it. Right. So just to summarise the pink box again in your book, if you take integral VT but time 2 minus time 1, put that into the function, you get your change in displacement. Making sense right at the moment. So what they've done then is they've increased it, so from 0 to 5 this time, and for whatever reason this particle changes direction, maybe it bounced off something, or I don't know. And we do 0 to 5, and this is where the numbers start changing, because if you integrate and put 5 and 0 in, you get an answer of 5. Okay? Now, we can see that that's different. So we've got displacement is 5, but what is the total distance travelled?
0.
No. What would be the total distance travelled by the particle at this stage? Okay?
I mean, let me. Should we do -4 plus 5?
Yeah, exactly. So it goes in this direction for 4. It turns around and goes back another
9.
9. So -1 up to 8. So if we have a look at the next thing, this is all in your book, just taking this out. So actually, look, we did the 3 to -1 gives you a displacement of 4, -4. But then it turns around and goes back to 8. So the total distance travelled is the 4 meters plus the next 9 meters. So we actually have 13. So we've got two very different values. So we notice in that first diagram here, up here, look, the displacement is 5. Okay? So the displacement is 5, but the total distance travelled is 13. Are we okay with that? Alright. So this then leads us to, how do we actually look at it when we talk areas under curves? Alright. So we started off with this function, which is t squared minus 4t plus 3, right? That leads us to this velocity function of 2t minus 4. Now you're happy with the 2t minus 4 for velocity. What have they done with s of t to get v of t? Differentiated. You got that answer? The first, we're on page 321 now. So the first function of t squared minus 4t plus 3, you see that was differentiated to give us vt 2t minus 4. Alright, now here's the thing. This graph, the first one, if you integrate and find the area under that curve, what value will you get? So this is, the x-axis is the time axis, so 0 to 5 seconds. Alright, why is the curve under the x-axis to start with?
Because it's going back.
Because it's going backwards. So we've got a negative velocity here, look. So this is a negative velocity. So it's underneath, and then at time 2 seconds, that's the point in which it turns and it's going back in the positive direction. So we've got two things to work out, obviously, displacement and distance travelled. So this curve here, when you work out the area here, what happens? Do you remember talking about that? So this would be a negative, this would be a positive, and they actually subtract from each other, so you end up with less total area, yeah? You all remember that, makes sense?
Yep.
So what we have then, if we actually want a total distance travelled, we've got to convert our graph, or at least think of it in this sense. Alright? So no longer when we apply it to a situation can we have a negative area. It doesn't do anything for us. Apart from that's displacement. The next curve shows you the total distance travelled. So what have they done with area A1? Brought it up. So instead of negative, they've just made it positive. So with total distance travelled, there is no requirement to have a negative area. Everything needs to be positive.
And with displacement, there has to be.
So with the displacement, you have to have the negative bits.
Because it shows the direction.
Yeah, exactly, because it shows direction. Total distance travelled, we need to have everything positive. Now that leads us to the one change in the way the function is written. Look, have you noticed the lines? And do you remember what that means? Absolute value, or modulus. Right? Make sense, everyone? Anyone not remember that? No? Okay, so you will see that here, look, I think it's running out of battery. If you take the absolute value of your displacement function, you will end up with your distance travelled. And in simplistic terms, what you're doing is any negative value has to become positive, and you just add it all together to get distance travelled. Simple as that. Right. So just finish on. Again, it's in your book. You can either think of it as a modulus function, or you can just think of it as any negative areas need to become positive. All right. What's the guys? What's the downside with your calculator now? Pardon? No, see, that's what I thought. Do you remember we had that issue with the negatives? Your calculator actually does work out negatives, doesn't it? And it takes it away. Yeah? So if you were to integrate a function using your calculator, you would get which one? The displacement or the distance travelled? Displacement. It will do the negatives and take it away. Okay? Do you know how to do absolute values on your calculator? So you can do an absolute.
Math, and there you have an option.
Okay, let's just check. So,
Yeah.
remember it? Math,
Number.
absolute. Okay. Now, can we just check if you put that into your graphing function, does that work? So let's try and graph that one in example 2t minus 4. So hopefully if we put math, number, absolute, it's just a paste, you get your little lines, and we would put in 2x minus 4. If you then graph that, right. How do we use our calculator to evaluate the integral? Remember?
Present, now,
Second calc, integrate f of x dx. Okay, we want it between 0 and 5. So x is 0, press enter, fine. Going to go across to, well, it doesn't give it me accurate, so I just press 5, x is 5, enter. So I've got the total distance travelled as 13, basically. Just a bit of an issue with the rounding, the accuracy of the screen for that. But 13 is agreed, as in the example in the book. If you change your function to get rid of the absolute and do 2x minus 4, which gives you displacement, do your graph. We have the same thing if we do second and calculate. Do your integral 0 and 5. You would get the answer 5. Okay. Right. Do you remember there were two ways? There were two ways to evaluate an integral. If you did.
I understand what you're doing. I just don't understand how you plug that into your calculator.
Yeah, I was going to remind you before you stop me. There were two ways to do the integrals, which I think someone said if we do math, okay, and then it was, which one was it?
9.
Math and number 9. You put that in, but that's not what we're using for this one, is it? All right, unless. You could, inside that function, then do math again and do absolute, and then you've got the same thing within there. So you've got two ways to deal with it. Okay? So the big thing, all I want to get across to you today is that that's the difference between dealing with displacement from a point and the total distance travelled. Alright? So, you can then, if you have a look through the other examples, you'll see as the graph goes, graphs of displacement with time can be straight lines and funny sections and all that kind of thing. It's easy enough to do. Basically, all you're going to have to work out is, do you add them all together as positives? Do you have to do subtraction? Which one is it you're going to be working out? So have a look through example 17, 18, and go on to the exam style questions. And then we'll basically be pretty much done with this section.
You mean integral?
Apart from trig functions. Right, off you go. Let you get on with it.